Okay, so here we have an example. It asks us to use the first derivative test to find all local extrema of this function. So I actually meant for this to be a different function, so I am going to cross this out and write in a different function, but I'll fix this on the notes. So it should be the correct function if you're using the PDF of the notes. Okay, so this is the function 2x cubed minus 9x squared minus 60x. Okay, and so we want to use the first derivative test, so our first step is going to be to take the derivative of this function. So since this is just a polynomial, we just use the power rule, and this will give us negative 18x minus 60. And then we want to factor this, so remember we're trying to find the critical numbers of this function, and then we will go ahead and create our sign chart and then find the local extrema. So we can factor 6 out of this, and we will be left with 3x minus 10, and then we can go ahead and factor this again. So we would get negative 5 and positive 2. And so setting this equal to 0, we'll get critical numbers at 5 and negative 2. Okay. So we will get, we will just put those on our number line, and then we want to create our sign chart for f prime. So we'll have a column for our test points, and then we have two factors. Remember that the 6, this is similar to the example we did at the beginning, the 6 is always going to be positive. It's not going to change the sign. So this time I'm just going to leave it off, not create a column for it, only create a column for the two factors that actually depend on x. So we'll have x minus 5 and x plus 2, and then that will determine the sign of f prime. Okay, so picking some test points, I'm going to take negative 3, 0, and 6. So those will represent each of my intervals. And then I will just go ahead and check this sign at each of those points. So at negative 3, we would get a negative number for x minus 5 and another negative number for x plus 2. At 0, we would get negative and positive. And then at 6, we would get positive and again positive. So we get positive, negative, positive. And so we can go ahead and put those on our chart. So we would get positive, negative in the center, and then positive. And so what happens is we get a local max at so notice that f is going to change from positive to negative at negative 2, so we get a local max there. And the way that I like to work this out, because I know it can be easy to flip it back and forth, so one way you get a local max, the other way you get a local min. So I like to draw arrows that represent whether the function is increasing or decreasing on an interval. So for this, the positive piece, the function's increasing, so I'll draw an arrow going that way just to imagine the way that the function is moving. Remember, this is f prime. So this corresponds to increasing, and then on the next interval the function will be decreasing, and then again increasing. And then it's a lot easier to see, and I can even, I'm actually going to draw these a little bit lower, the same idea. It's a lot easier to see that if you were to follow a function that were moving like this, there would be a max right there where it switches from increasing to decreasing. And then there would be a min when it switches from decreasing to increasing. So we get a local max at x equals -2 and a local min at x equals 5. And that is by the first derivative test. When you use the first derivative test, you don't need to write down that you're using it. You can just go ahead and make the conclusion. So this would be our answer. That is our local extrema for this function. Okay, and so the last thing that we're going to talk about in the first part of this section, so we'll have to do a second part for the rest of it, but so we can use actually the second derivative to test a function for concavity. And so this is saying that if the second derivative is greater than 0 on an interval, then f is concave up on that interval. And if f is, f double prime, if the second derivative is less than 0 on an interval, then f is concave down on that interval. So this is really very similar to what we started out talking about, which was the function increasing or decreasing. So what this is telling us is that the first derivative tells us about whether f, the function, is increasing or decreasing, and the second derivative tells us what the concavity of f is. Okay, so just very generally, that's the information that we get from the first derivative versus the second derivative. And remember that concave up was, so you can just think of a parabola. A parabola facing upwards is concave up, and then a downwards facing parabola is concave down, right? And so the way that I like to remember which one corresponds to f double prime being positive or negative is to, so I'll just go ahead and draw this down here. So if f double prime is greater than 0, you get concave up, and you can remember this by this. So it's a smiley face if you get greater than 0. So if you have positive second derivative, and then if f double prime is less than 0, you get concave down, which is an unhappy face and looks like this. And so I know it's silly, but it should help you remember this. So I'm not going to do an example, but we will do some practice in class. And it's really going to be very similar to the examples that we've done using the first derivative, but we'll have to find the second derivative. And then once we find the second derivative, we follow the same method of using the sign chart to determine intervals where the second derivative now is positive or negative. Okay, so that is all for this section, and don't forget to do the comprehension check.